Explanation: an AVL tree is a binary search tree, abbreviated BST, that also obeys a height balance rule. Formally, for every node x in the tree, let h sub l of x be the height of its left subtree, and h sub r of x be the height of its right subtree. The tree is an AVL tree if and only if for every x we have absolute value of h sub l of x minus h sub r of x less than or equal to 1. This condition is called the balance invariant. It guarantees that the tree never becomes too tall on one side, keeping operations search, insert, delete logarithmic. Think of a seesaw. Each node is the pivot, and the two sides, left and right subtrees, must stay within 1 unit of height, otherwise the seesaw tips and the structure becomes unstable. The AVL definition adds this mechanical stability rule on top of the ordinary BST ordering: left keys less than node key less than right keys. The balance factor BF of a node x is defined as BF of x equals HL of x minus HR of x. Because of the AVL invariant, BF can only be -1, 0, or +1 for a correctly balanced node. The height of any node satisfies the recurrence. H of x equals 1 plus the maximum of HL of x and HR of x, with the base case h of null equals -1 or 0 depending on convention. This recurrence lets us compute heights bottom up. For example, if a node has left height 3 and right height 2, its height is 1 plus max of 3 and 2 equals 4, and its BF equals 3 minus 2 equals +1, which is still allowed. When BF becomes +2 or -2, we have detected an imbalance and must rotate to restore the invariant. The recurrence also explains why AVL trees are shallow. Each time we go down one level, we at most lose one leaf on the shorter side, leading to the Fibonacci-like growth of the minimum number of nodes for a given height. Explanation: the LL rotation, also called a right rotation, fixes a situation where a node Z has BF equals +2 left heavy, and its left child Y has BF equals +1 also left heavy. Visually, it looks like a left-leaning staircase that needs to be straightened. A procedure: 1. Let y equals z dot left, t3 equals y dot right. 2. Make y the new root of the subtree. 3. Set z dot left equals t3. 4. Set y dot right equals z. Function rotate right open parenthesis z close parenthesis newline y equals z dot left newline t3 equals y dot right newline y dot right equals z newline z dot left equals t3 newline comment update heights newline z dot height equals 1 plus max of height of z dot left, and height of z dot right newline y dot height equals 1 plus max of height of y dot left, and height of y dot right newline return y. Proof of height reduction: before rotation, height satisfy h of z equals 1 plus max of h of y, h sub r of z, and h of y equals 1 plus max of h sub l of y, h sub r of y. Because the imbalance is LL, we have h sub l of y greater than or equal to h sub r of y, and h sub l of y equals h of z minus 2. After rotation, the new root y has left height h sub l of y unchanged, and right height h of z becomes 1 plus max of h sub r of z, h sub r of y. The new height of y is 1 plus max of h sub l of y, 1 plus max of h sub r of z, h sub r of y. Since h sub l of y equals h of z minus 2 and h sub r of z less than or equal to h of z minus 1, the new height of y drops to at most h of z minus 1. Thus the subtree height shrinks by at least 1 comma, restoring the balance invariant. Explanation: the RR rotation left rotation mirrors the LL case. It is triggered when a node Z has BF equals -2, right heavy, and its right child Y has BF equals -1, right heavy. The shape resembles a right-leaning staircase. A procedure: Number 1, let y equals z dot right, t2 equals y dot left. Number 2, make y the new root of the subtree. Number 3, set z dot right equals t2. Number 4, set y dot left equals z. Pseudocode: function rotate left open parenthesis z close parenthesis y equals z dot right, t2 equals y dot left, y dot left equals z, z dot right equals t2. Comment update heights: z dot height equals 1 plus max of height of open parenthesis z dot left close parenthesis, height of open parenthesis z dot right close parenthesis. y dot height equals 1 plus max of height of open parenthesis, y dot left close parenthesis, height of open parenthesis, y dot right close parenthesis. Return y. Proof of height reduction colon symmetric to the LL proof. Before rotation, h of z equals 1 plus max of h underscore L of z and h of y, and h of y equals 1 plus max of h underscore L of y and h underscore R of y, with h underscore R of y equals h of z minus 2. After rotation, the new root y gets left child z, whose height becomes 1 plus max of h underscore L of z and h underscore R of y. Because h underscore R of y equals h of z minus 2 and h underscore L of z less than or equal to h of z minus 1, the new height of y is at most h of z minus 1. Hence the subtree height drops by at least 1, eliminating the imbalance. The left-right double rotation repairs a node z that is left heavy. Balance factor equals plus 2, but whose left child y is right heavy, balance factor equals minus 1. The subtree looks like a zigzag, a left step followed by a right step. The fix is a two-step process. First a left rotation on y, then a right rotation on z. Step 1, y equals z dot left, x equals y dot right, the middle node. Step 2, perform rotate left on y, turning x into the left child of z. Step 3, perform rotate right on z, turning x into the new root of the whole subtree. Function rotate left right of z colon. Y equals z dot left. X equals y dot right. Comment first rotation left on y. Y dot right equals x dot left. X dot left equals y. Comment second rotation right on z. Z dot left equals x dot right. X dot right equals z. Comment update heights bottom ups. Y dot height equals 1 plus max of height of y dot left and height of y dot right. Z dot height equals 1 plus max of height of z dot left and height of z dot right. X dot height equals 1 plus max of height of x dot left and height of x dot right. Return x. Proof of height reduction. Before rotation, the heights satisfy h of z equals 1 plus the maximum of h of y plus 2 and h right of z, and h of y equals 1 plus the maximum of h left of y and h right of y, with h right of y equals h left of y plus 2. After the two rotations, x becomes the root with left height equal to h left of y and right height equal to h right of z. Both sides differ by at most 1, and the new height of x is 1 plus the maximum of those, which is at most h of z minus 1. Thus the overall height drops by 1, satisfying the AVL invariant. The RL rotation right-left double rotation is the mirror of LR. It occurs when a node z is right heavy, balance factor equals minus 2, and its right child y is left heavy, balance factor equals plus 1. The shape is a right step followed by a left step. A procedure. Step 1, y equals z dot right, x equals y dot left. Step 2, perform rotate right on y, turning x into the right child of z. Step 3, perform rotate left on z, turning x into the new root of the subtree. Pseudocode. Function rotate right left taking z. Y equals z dot right. X equals y dot left. First rotation right on y. Y dot left equals x dot right. X dot right equals y. Second rotation left on z. Z dot right equals x dot left. X dot left equals z. Update heights bottom up. Y dot height equals 1 plus max of height of y dot left and height of y dot right. Z dot height equals 1 plus max of height of z dot left and height of z dot right. X dot height equals 1 plus max of height of x dot left and height of x dot right. Return x. Proof of height reduction. Symmetric to LR. Before rotation, the right subtree of z is taller by 2 levels and its left subtree of y is the heavy part. After the two rotations, the middle node x becomes the root with balanced left and right heights, each at most 1 less than the original height of z. Consequently, the subtree height drops by at least 1, restoring the AVL balance property. When inserting a key into an AVL tree, we first follow the ordinary binary search tree insertion path until we reach a leaf position. After insertion, we walk back up the recursion stack, updating the height and checking the balance factor at each ancestor. There are 4 possible cases for an unbalanced node Z, where the absolute value of the balance factor equals 2. LL inserted into the left subtree of the left child, balance factor equals +2. Left child balance factor is greater than or equal to 0, which requires a single right rotation. RR inserted into the right subtree of the right child, balance factor equals -2. Right child balance factor is less than or equal to 0, which requires a single left rotation. LR inserted into the right subtree of the left child, balance factor equals +2. Left child balance factor equals -1, which requires a double rotation. First a left rotation on the left child, then a right rotation on node Z. RL inserted into the left subtree of the right child, balance factor equals -2, right child balance factor equals +1, which requires a double rotation. First a right rotation on the right child, then a left rotation on node Z. Only the first unbalanced node encountered on the upward walk needs rebalancing. After performing the appropriate rotation, the height of that subtree is reduced, so higher ancestors remain balanced. Thus the insertion algorithm runs in big O of log n time. A logarithmic search to find the insertion spot plus constant work at each level on the way back. The insert function takes a node and a key. If the node is null, it returns a new node containing the key. Otherwise, if the key is less than the node's key, it recursively inserts into the left subtree, else it inserts into the right subtree. After the recursive call, it updates the node's height, computes the balance as the height of the left subtree minus the height of the right subtree, and then checks 4 conditions. If the balance is greater than 1 and the key is less than the left child's key, it performs a right rotation LL case. If the balance is greater than 1 and the key is greater than the left child's key, it first left rotates the left child and then right rotates the node LR case. If the balance is less than -1 and the key is greater than the right child's key, it performs a left rotation RR case. If the balance is less than -1 and the key is less than the right child's key, it first right rotates the right child and then left rotates the node RL case. Finally, it returns the possibly rotated node. Deletion in an AVL tree is more subtle because removing a node can cause a cascade of height reductions, potentially unbalancing many ancestors. The steps are: 1. Perform ordinary BST deletion. Replace the node with its in-order predecessor or successor when it has 2 children. 2. On the way back up the recursion, update each node's height and compute its balance factor. 3. If a node becomes unbalanced, BF equals 2, we apply the same 4 cases as in insertion. But the child balance factor is examined after the deletion, not based on the inserted key. The appropriate rotation LLRR restores balance at that node. 4. Propagation. After a rotation, the height of the rotated subtree may decrease by 1, which can cause its parent to become unbalanced as well. Therefore, we must continue checking ancestors up to the root. In the worst case, a rotation may be needed at every level, leading to O of log n rotations. Complexity: each step searching for the node, deleting, updating heights, checking balance costs O of log n. Since at most 1 rotation per level is performed, the total work remains O of log n. Pseudocode high level. Delete node key. If node is null, return nulls. If key less than node.key, set node left to delete node left key. Else if key greater than node.key, set node right to delete node right key. Else, node with 1 or 0 children. If node left is null, return node right. If node right is null, return node left. Node with 2 children, replace with in order successor. Suck equals minimum value node of node right. Node.key equals suck.key. Node right equals delete node right suck.key. Update height of node. Balance equals height of node left minus height of node right. Rebalance cases same as insertion. If balance greater than 1. If height of node left greater than or equal to height of node left right. Return rotate right of node LL case. Else, node left equals rotate left of node left, LR part 1. Return rotate right of node, LR part 2. If balance less than -1. If height of node right greater than or equal to height of node right left. Return rotate left of node RR case. Else. Node right equals rotate right of node right, RL part 1. Return rotate left of node RL part 2. Return node. The key insight is that deletions may propagate upward, while insertions stop after the first rotation. Explanation: typical exam problems test both theory and practical skills. 1. Height-bound derivation. Show that an AVL tree with n nodes has height h less than or equal to 1.44 log base 2 of n plus 2 minus 0.328. The proof starts by defining n of h, the minimum number of nodes in an AVL tree of height h. The recurrence is n of h equals 1 plus n of h minus 1 plus n of h minus 2, with n of 0 equals 1, n of 1 equals 2. This is the Fibonacci sequence shifted, giving n of h equals f sub h plus 3 minus 1. Using the closed form, f sub k approximately phi to the k divided by square root 5, where phi equals 1 plus square root 5 divided by 2, we get n of h approximately phi to the h plus 3 divided by square root 5. Solving for h yields h less than or equal to log base phi of n times square root 5 minus 3, approximately 1.44 log base 2 of n plus 2. 2. Construction from a key sequence. Given a list of keys, students must insert them into an AVL tree, indicating after each insertion whether a rotation left-left, right-right, left-right, or right-left is required. Example, insert 30, 20, 10. After inserting 10, node 30 becomes unbalanced with balance factor plus 2 and left child balance factor plus 1. Perform left-left rotation. 3. Identifying required rotations. Provide a partially built AVL tree and ask which rotation will fix a given imbalance. The answer is found by looking at the sign of the imbalance at the grandparent and the direction of the heavy child. For example, balance factor minus 2 at Z with right child balance factor plus 1 implies right-left rotation. 4. Proving rotational correctness. Students may be asked to prove that a left rotation preserves the binary search tree ordering. The proof argues that all keys in Z's left subtree remain less than or equal to Z less than keys in Y's right subtree. And after rotation, Y becomes the root with Z as its left child, preserving the ordering because Z's keys are still less than or equal to Z less than or equal to keys in Y's right subtree. These questions combine algebraic reasoning, Fibonacci bound, algorithmic simulation insert and rotate, and formal proof preservation of order and height reduction, covering the full spectrum of understanding required for AVL trees.